some other people will join as they have time, but we'll start talking a little bit more about factoring. So, a little bit is what French and I have already started talking about as greatest common factor, or I mean as factor by grouping, but we'll start with the greatest common factor, then more factor by grouping. We'll look at factoring trinomials 2 different ways, and then difference of squares. So what is the greatest common factor? The definition is it's the largest common integer and variables of some set of numbers. So for example, if we're asked to find the greatest common factor of 36 and 24, we want to start perhaps by listing all of those factors of 36 and 24. So 36 would be 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. Those would be our factors of 36, and similarly we can look at our factors of 24. 1 and 24, 2 and 12, 3 and 8, and 4 and 6. We can see that we have many factors in common between these 2 numbers. Obviously, 1, 2, 3, and 4 are in common between each of them. 6 is in common. 8 is not in common, but then 12 is in common. And indeed, 12 is actually our largest number, our largest factor that's in common, so we would consider that the greatest common factor. So the greatest common factor of 36 and 24 is 12. There's a lot of other methods that we could use to get to that. We could go to prime factorization, but this is one method that I think is helpful, especially when we continue on into factoring. We're always going to be looking to list out factors of certain numbers. So then, if we take this idea of 36 and 24 and say, well, what if we have 36x squared y cubed and 24x to the 4th y squared? Well, we could look at this a couple ways. One way to see this is that it's 12 times 3 and 12 times 2. This is our 36x squared y cubed, and this is our 24x to the 4th y squared. We can see that 12 is in common for both of these numbers, or expressions. And then we look at the x's, and we see we have x squared in common. We have 2 x's in common in these expressions. And likewise, we also have 2 y's that are common in these expressions. So what we see then is we have 12 times x times y, or 12 x squared y squared is our greatest common factor. And this is just kind of a nice way if we draw it all out to see what those greatest common factors are. But how can we do this? How can we factor without writing everything out? Jane, it's wonderful to have you join this session. I hope you can hear me. Please either give me a chat or something so that I know you can hear me as we continue on. But welcome. So how can we figure out, again, what the greatest common factor is, specifically with variables without writing everything out? Well, what we're going to look at is the idea that x squared here is a perfect square, or x squared here, and x to the 4th. If we look at just these 2 things, we notice that x squared is smaller than x to the 4th, but it's still the largest number of x's that we can take out, okay, in x squared. Similarly, when we look at our y cubed and our y squared, again, is the largest that we can take out of both of them. So what we're actually doing, it seems kind of weird that we're looking for the smallest exponent, but the smallest exponent is going to be the largest amount that we can take out of all of the expressions. So I know that's kind of confusing, so let's take another peek. I want you to try to find the greatest common factor of the following. 42 s to the 13th t squared, 63 s to the 12th t to the 4th, and 21 s to the 15th t cubed. If you were just trying to find the greatest common factor, what would it be? And I have our poll set up now for A, B, and C. What would that greatest common factor be? And if you haven't used the poll feature before, the poll is, if you look above the main room, you see a smiley face, a little person with a clock for away, a hand to raise your hand, and then an ABC. And that ABC allows you to poll in. Okay. Yes, Jean, question. You can push the talk button or you can chat, but go ahead. Okay, or I see you have found the poll button. Very good. Okay, you all have polled in. And it looks like we are all on the same page, recognizing that the greatest common factor is 21 s to the 12th t squared. So again, if we look at 42, 63, and 21, 21 is the largest, the greatest common factor that goes into all three of those numbers. Then if we look at our s's, we have s to the 13th, s to the 12th, s to the 15th. So since s to the 12th is the smallest of those variable exponents, then we know that that is the greatest factor, okay, s to the 12th. Likewise with the t's, we have t squared, t to the 4th, t cubed, and we can only take a t squared out of everything. So good. Very nicely done. So once we find the greatest common factor, what we want to do is figure out what we have left over after factoring it out. So for example, we have 8m plus 24. What we can see is that 8 is in common. It is our greatest common factor between these two expressions. And so I've kind of highlighted that in red here. You can see then that if we factor out that 8, what we are left with is what's in gray, m plus 3. So the factored form of 8m plus 24 is 8 times m plus 3. And we can distribute. We can always distribute or multiply back in to make sure we have the exact same thing. So what we see is we take 8 times m, 8 times 3, and sure enough that gives us back to the original of 8m plus 24. So that's what we're looking to do in factoring. We're looking to use that greatest common factor, take it out, and see what we have left over. So let's go ahead and practice. First, I want you to think about this for a little bit, and then let me know what is the greatest common factor. Once you figure it out, go ahead and type in what is the greatest common factor in the chat feature here. Go ahead and type in what is that greatest common factor of this expression. Okay, French has said is 7a to the 5th, b to the 22nd. Peter and Jane, what are your thoughts? Okay, excellent. So it looks like we agree with that. The idea then is our greatest common factor is 7, a to the 5th, b to the 22nd. okay? And so what we do now is we say, well, if we take 7, a to the 5th, b to the 22nd, and factor it out, we want to figure out then what we have remaining. And so in essence, what we're doing is I'm saying, well, I'm going to take 7, a to the 5th, b to the 22nd. It's almost like I'm dividing each expression by it, okay? Because I want to know what I would have to multiply it by to get back to that same thing. So if you need to think of it, we're almost saying if I factor that out, I'm in essence sort of dividing it to see what's left over. So then we have 42 divided by 7 is 6. If I take a to the 5th out of a to the 13th, I'm left with a to the 8th power. And if I take b to the 22nd and I divide b to the 22nd or factor that out, I'm left with 1. So first what's left over is 6a to the 8th. I'm subtracting from that. Well, 14 divided by 7 is 2. A to the 8th divided by a to the 5th would give me a to the 3rd power. And b to the 31st, and if I take b to the 22nd out, there are b to the 9th remaining. And then in my third term, 21, I take 7. Again, I'm thinking factoring it out, so I'm dividing, in essence dividing, so that I can rewrite this as a multiplication. I have 3. The a to the 5th divided by a to the 5th is 1. And then b to the 25th divided by b to the 22nd would leave me with b to the 3rd power. Sorry, that's 3, that b got a below there. Okay, so that is what we're going to be looking at. We're going to take and factor expressions, and this is factoring through the greatest common factor. Are there any questions about that before we go on? Wendy, it's good of you to join. Nice to see you today online. So that's greatest common factoring. Again, any questions before I continue on? Oh, saw that. Thank you, Wendy. All right. So factor by grouping. We've been looking at some examples where there's always something in common between, the 2 or the 3 terms that we have. But sometimes we want to factor, and we don't always have the common terms in there. So we're going to look at an idea called factor by grouping, which is really helpful. So what is factor by grouping? Well, first what we want to do is we want to ask, is there a greatest common factor that we can take out of all 4 terms? So I'm going to change our poll to a yes or no. And I want you to let me know, is there a greatest common factor, yes or no, that we can take out, we can factor out of all 4 of these terms? Go ahead and poll in. Go ahead and poll in a yes or a no there. Okay. Is there a greatest common factor? Yeah, I know some of you are typing it in. Okay. So most of you then have either typed in or have expressed that no, there is not a greatest common factor. Okay? And so what we're going to have to do is we're going to have to work on this idea of factor by grouping. Now, there's going to be times where we factor by grouping and sometimes have a greatest common factor. Well, what is in common? Okay? Well, I can see that 5c minus 5d, there's a 5 in common there. So I'm going to look, what if I grouped those first 2? Now, by adding those parentheses, by adding parentheses in, have I changed this problem? Okay. I have not changed this problem at all. Adding in this parentheses, it still says take 5c minus 5d plus cd minus d squared. All I've done is said, hey, what if I put those in parentheses? I want to look at that first. I'm going to do the same thing with the second 2 terms. I'm going to say I'm going to add to that CD minus D squared. And all I've done now in order of operations is given myself some priorities. So I've said, hey, what if I took this 5C minus 5D and then said, okay, let's do CD minus D squared. Now that I've grouped these things, notice I just grouped the first two and the second two terms, but there's still an addition sign in between here. That's really important. I have not changed this problem yet. I'm now going to factor out the greatest common factor from the first set of terms. And I'm going to factor out the greatest common factor from the second set of terms, which is D, leaving me C minus D again. Okay? Now that I've done that, something to notice is that the C minus D is the same factor in both cases. It's saying take 5 and multiply it by C minus D, and take D and multiply it by C minus D. And what's really great about this then is that we can actually group this into two binomials. We can say that in essence what we're looking at is 5 plus D times C minus D. So notice I've taken this 5 and this plus D and combined it into one binomial. Now, why does this work? It's always important. We might just say, okay, we know we can do this, but why? Why does this work? Well, when we're at this step, we know to check it that we could FOIL or multiply. So let's look at that. If I multiply, I have 5C minus 5D. Then if I multiply, I get plus DC, which I'm going to rewrite as CD. So I go in alphabetical order, and minus D squared. This should look very familiar. 5C minus 5D plus CD minus D squared, well, that's our original problem. It's our original problem. So what this is showing me is that this grouping is really telling me at this step here, take 5, multiply it to C minus D. Well, that's the first part of FOIL, right? That would be our first and our outer. Take 5 and multiply it to C, and 5 and multiply it to negative D. Then, the rest of our FOIL, our inside and our last, is the second part. Take D and multiply it to C minus D. And that's what we did here, D to C and D to minus D. So what we've kind of done is reverse engineered our understanding of FOILing, okay, so that we could factor this through a process of grouping. Okay, see that there's lots of colors. I've gotten really excited because this is my favorite way to factor. Does that process make sense? Why don't you just give me kind of a yes, no. Is that process making sense? How we grouped. So we took and we grouped the first two terms and the second two terms, factored out what's in common for both of those, and then rewrote it as two binomials being multiplied together. Okay, good. I see most of you are with me understanding it. Well, we'll look at a couple more examples so that you feel a little more comfortable with it. Okay, so again, let's look at this one. And I will have you kind of work through it. Again, we want to think about grouping these first two terms and these second two terms. Okay, and what happens then? If you group those and you continue with greatest common factoring, once you figure it out, go ahead and pull in A, B, or C. What do you end up with? What do you end up with when you factor these by grouping? Okay, most of you have pulled in, so I'm going to publish and see where we're at. And it looks like we mainly chose A with a little bit choosing B here. So let's go through this and make sure we're all on the same page. Once I have factored this idea, 2x cubed plus x squared, I'm going to take out the greatest common factor of an x squared. What's remaining then is I have a 2x. And when I take an x squared out of an x squared, what I'm actually left with then is plus 1. And then I need to take the greatest common factor out of 2x plus, or 12x plus 6. I'm actually going to take a 6 out of that. And when I take a 6 out of that, I will be left with a 2x plus 1. And then how this factors together then, how this groups together, is I have x squared plus 6 as one of my factors, and 2x plus 1 as another factor. Now, we know in multiplication that A times B is the same as B times A. Again, A and B can stand for anything. In this case, they stand for a whole binomial. X squared plus 6 times 2x plus 1 is the same as A. 2x plus 1 times x squared plus 6. Okay? Good. So most of you are pretty on page with this. All right. Now we get into something a little trickier. Okay, we have some negatives that we need to deal with. And so I want you to think through what is the difference in these following groupings. I've given you 4x squared plus 6x minus 10x minus 15. Okay, I want you to think through A, B, and C here. I grouped them 3 different ways. Which way is correct? That's what I want you to think about. Which way is correct? And then we'll talk about, well, what are the differences in these groupings? How do I know which way is correct? Okay, about half of you have polled. I'll give you another couple of seconds to see if you can't figure it out. If not, I urge you just to take a guess, and then we'll chit-chat about it. What's your instinct? What are you thinking? All right, well, let's publish this and see if we can't figure it out. Okay, most of you have chosen C. Some people looking at A and a couple people not sure. So, okay, as we look through this then, all right, as we look through this first, no one chose B. Let's talk about why B is not correct. Go ahead and if you can explain through the chat feature, if you want to talk to me, you're more than welcome to hit the talk button in chat. But why is B not correct? We know that this is not correct. There's kind of a major reason it's not correct. Okay, good. French has kind of given us a little bit about A. I'll continue on with B and then we'll go back to A. All right. A couple people typing in. Good, good. See some more people. Good. So a lot of you, French and Wendy and Jane, all came up with the idea that B is showing a multiplication. B is showing a multiplication, which is not what we are working on right now, in essence. It changes the original problem. The original problem is not telling us to multiply these two binomials. It's saying here's four terms that we're adding and subtracting together. A then, as French pointed out, says it's wrong because if we take this negative and we distribute it back into the original problem, we would end up with a negative 10x, which is correct, but then a positive 15. So in A, we've changed the problem. Okay, it looks fairly correct because all I've done is thrown those parentheses in, but we've changed that problem, and we can't do that. We're always looking in mathematics to keep these things equivalent. Okay, so C is the correct answer. Okay, C is the correct answer, and the reason is because we have not changed the problem. If I look and I distribute, well, a positive, or a positive 1, I haven't changed this problem at all. So now what I want to do is I want to continue with grouping and figure out what is the factored expression. So I would factor out a 2x from my first expression, leaving 2x plus 3. Now, in my second expression, I want to make sure I get the exact same thing. I want to get 2x plus 3. So I'm still looking at maybe what is the greatest common factor, but in this instance, I'm also needing to take out a negative. So I'm actually going to take a negative 5 out of everything because I want to end up with a positive 2x and a positive 3. Because now that I have this, I see 2x plus 3 is the same in both of these. So I'm going to rewrite it as first the coefficients, 2x minus 5, multiplied by 2x plus 3. All right, very nice. Okay, so that's factor by grouping, and now we're going to go on to looking at factoring trinomials. And first we just need to recall what we used to do when I asked you to multiply two binomials. When we were multiplying, we were looking at distributing, or we use that acronym FOIL to help us, right? So when we do that, we have x squared plus 2x plus 3x plus 6. Or combining like terms, we get x squared plus 5x plus 6. Well, now what we want to do is we want to take our answer of x squared plus 5x plus 6 and work backwards to get those binomials of x plus 3, x plus 2. So we're trying to see if we can't say, here is what we have as an expression, x squared plus 5x plus 6. Can you find it in factored form? And what's going to be really important to notice then is this idea that 3 times 2, when we had a 2x and a 3x, we were adding them to our middle term. And at the end, our L, our FOIL part of this, we were multiplying. So the idea of looking for addition and multiplication is going to come into play when we factor. So factoring trinomials, again, such as something like x squared plus 7x plus 12, back into binomials. That's what we're doing. And we need to recognize that the x squared has a coefficient of 1. That's kind of, we're going to be looking at two methods. This first method is where we have a coefficient of 1, and the second method will be where we have a coefficient other than 1. So steps. So what we want to look at first is that constant. So we want to list all the pairs of numbers that multiply to equal that constant of 12. So again, finding those factors, 1 times 12, 2 times 6, 3 times 4, is important. Then, once we have found the pair that multiplies, again, multiplies to 12, we want to find that, we want to look at what pair of number then adds to our middle coefficient. And that would be 3 and 4. Okay. Now this is kind of odd. I tell you just to fill in the blanks, right? We're just taking that 3 and that 4 and filling it into these blanks because we know a binomial looks something like this. Now, where did these blanks come from? Let's go back, okay? When we were multiplying, we were looking at x plus 3 times x plus 2. We started with the idea that x times x gives me x squared, okay? Then we found our positive 3 and our positive 2. We recognized that those two would add to our middle term and multiply to our last term. So what happens here? Well, we recognize x squared. We look at that x squared and we see that, well, if I FOIL this thing, I would get x squared plus 4x plus 3x. And that plus 4x plus 3x from our outside and our inside add to 7. Again, that's why we're trying to find something that adds to the middle two terms, and then last 3 times 4 multiplies to our last term. Okay? So, with factoring, again, we're going to be looking for what multiplies, okay? What is a product there? What multiplies to 12, and what adds to our middle term, in this case 7. So this is going to hold true for any trinomial that has a constant of 1, okay, or a coefficient of 1 of the x squared term. So we have to be careful though, because our constant in this case is negative. So that means we need to list all the pairs of numbers that multiply to equal a negative 24. And if we're multiplying to a negative, that means that one number has to be positive and one number has to be negative. So here I've listed all of those pairs of numbers. So I said 1 times 24 is 24, but one of them can be negative each time. 2 times negative 12 or negative 12 times 2. 3 times negative 8 or negative 3 times 8, and 4 times negative 6 or negative 4 times 6. And which pairs of numbers add up to a positive 2? That's what we're looking for. Okay, well the pairs of numbers that add up to that positive 2 are 4 and a negative 6. And we know that we are looking at x squared, okay, so and we're putting this into some sort of binomial. So x squared would give us x times x. But we're multiplying to a negative 4, adding to a positive 2. We said that, oops, I didn't even stop me. We're adding to a positive 2. Oh, adding to a positive 2 would mean that I need 6 and a negative 4, right? So I would be adding 6 and subtracting 4. You can always catch me. Sometimes I say things wrong. And then we should always FOIL or distribute to make sure that we have this correct. So we can see now x times x is x squared. X times a negative 4 gives me a negative 4x and a positive 6x. And a negative 24. Okay, and there's where our negative 4x and our positive 6x combine together to make a positive 2x. X squared plus 2x minus 24. Okay, so that works out. Now we're going to look at factoring trinomials, but there's going to be something a little bit different about these ones. Okay? In this case, we have a leading coefficient other than 1. Our leading coefficient here is 3. So we're going to look at kind of a different method. Often students have learned guess and check. they've learned to do something like this, where you have a 3x and an x, because you know that 3x times x will give you 3x squared. And then they're going to guess and check what the remaining piece is. That works out, but it's not always the most efficient strategy. So I'm going to show you a different strategy to figure out how to factor these things. And this strategy also works when you have a coefficient of 1. What you're going to do is you're going to multiply the leading coefficient, in this case 3, by the constant, in this case 8. So we have 3 times 8 is 24. We want to list the pairs of numbers that multiply to equal this newfound product of 24. So note, we're not just looking at 8, our constant, we're looking at our leading coefficient times our constant, which is 24. And so we look at 24 and we figure out what pair adds up to 14. And that would be 2 times 12. Okay, so what's been a little different right now is we've started off with multiplying 3 times 8 to give us 24. Then we've done kind of a similar method, listing the pairs of numbers that equal that 24, figuring out what adds up to the middle term. But that does not mean we can just put a 2 and a 12 into these blanks. Okay, that's not going to help us. So what are we going to do? Well, we're going to rewrite the pairs of numbers that we found. Remember, we found 2 and 12. Okay, 2 times 12 multiplies to 24 and adds to 14x. So we're going to rewrite this as 3x squared plus 12x plus 2x plus 8. And the big question is, have I changed this problem? Okay, have I changed the problem? Is anything different? What do you think? Yes or no? Have I really changed this problem? Okay, you can give me a poll response, a yes or no. You can. Okay, good. So some people have polled in, have typed in no. I really haven't changed this. All I said is 12x plus 2x is 14x. And that's important to note. Okay, I've just rewritten it, but I haven't changed the problem. Well, now we have 4 terms, and we know a method to factor when we have 4 terms, and that's factor by grouping. So now if I group these and take out the greatest common factor, I'm going to take a 3x out of my first set of terms, leaving x plus 4. And I'm going to take a 2 out of my second set of terms, leaving x plus 4. Meaning that what I really have then is 3x plus 2 times x plus 4. So this method where we took the leading coefficient of 3, multiplied it by 8, our constant, and then rewriting the middle 2 terms is really effective because it's going to work every single time. Okay, it's going to work every single time. And as always, we can check to make sure this works. By distributing, we would have 3x squared plus 12x plus 2x plus 8. And you can see there's our 12x and our 2x that we wrote before. So this method just kind of reverse engineers our understanding of multiplying binomials by rewriting it again as what multiplies to our constant of 8 and adds up to the middle coefficient. We just have to take into consideration that leading coefficient. Okay, and again, there's my factoring and my checking for understanding. Okay, so I want you to look at this one. Again, think first we need to figure out what pairs of numbers add to our product of negative 12. So we take 3 times the negative 4 to give us a negative 12. Listing the pairs of numbers that multiply to equal that negative 12, what pair adds up to a negative 11? Go ahead and type it in if you figured it out, what multiplies to a negative 12 but adds up to a negative 11. Good. Wendy said it's 1 times negative 12. Good, good, good. So now what we want to do is we need to rewrite that. Oops, we'll finish it up here, yes. We need to rewrite that then as 3x squared minus 12x plus x minus 4. Now, does it matter if I would write this as 3x squared plus x minus 12x minus 4? Does it matter what order I write those middle two terms? Okay, so I've written it negative 12x plus x or plus x minus 12x. What do you think? Is it going to change my problem at all? Going to change my answer? Why don't you work through it and see? Okay, some of you have pulled in, some of you have typed in. No, this is not going to change my answer. I'll factor this second one here. Grouping, I'm going to group those first two. Be really careful about grouping those second two. I'm going to put that addition sign in between there and leave that negative on the inside. Grouping, I have an x, that's the only thing that's in common from my first two terms, leaving 3x plus 1. Then I'm going to take out a negative 4. And in taking out a negative 4, I'm again left with 3x plus 1. And finally then, putting this together, I get x minus 4 times 3x plus 1. Okay, so that's factoring trinomials. We've looked at it where we have a coefficient of 1 and a coefficient other than 1. So lots to do with factoring so far. We have just one more topic to talk about, and that is looking at the idea of difference of squares. Okay, and this is again just a recall. When we multiplied the sum and difference of the same two numbers, so we have the same two numbers or variables, x and 6, and we have a sum and a difference. When we multiply those out, we ended up getting x squared minus 6x plus 6x minus 36. And what we notice is that those middle two terms every time added to 0x. And because of that, we got this wonderful thing of just x squared minus 36. Now, did we ever have two binomials that multiplied to x squared plus 49? Do you ever recall two binomials? If you do, please give me the example. What binomials did we have multiplying to x squared plus 49? Did we have any? What do you think? Okay, some of you have polled. Yeah, Wendy's saying there was always a middle term. So the common response that I normally get is something like this: x plus 7 quantity squared. My students always think we take and we square over the x and we square the 7. Okay, but no, we cannot do that. We need to look at that as x plus 7 times x plus 7. Really, that was being the whole binomial being squared. And as Wendy said then, there's always going to end up being that middle term. We would get x squared plus 7x plus 7x plus 49. And because of that, we always have this middle term, in this case 14x. So no, we did not have a sum of squares that we worked with. So what that means, though, is that we are going to work with this subtraction sign, or difference. Okay? So we need to talk about factoring this difference of squares. Okay? So before we had x squared minus 36, now we're looking at x squared minus 9. Okay? X squared minus 9. We can recognize this as a difference of squares. The difference of squares comes because x squared is a square, a perfect square. 9 is a perfect square. And there's our difference, right? There's our subtraction sign. So recognizing this, we know that it factors into x plus 3, x minus 3, right? We have that sum and difference of the same two terms. And if we forget, or if we're not sure if that's right, go ahead and again, multiply or FOIL that thing out to get x squared plus 3x minus 3x minus 9. And again, you can see here's my middle two terms. They add up to 0x. So if you want to think of it, you can go back to how we worked with binomials or with trinomials and said, okay, well, it multiplies to my first term or my last term of a negative 9, my constant of a negative 9, and adds up to my x term, my middle term, but the middle term here is 0x. So that's, you know, really you can either, again, just use the recognition idea, or you can still think of it as factoring out, just looking at it as a trinomial, and the trinomial where your middle term is 0x. Okay? So here, I got these out of order a little bit. We're going to start with factoring these difference of squares, then we'll end up with some more trinomials. So go ahead, I want you just to practice the first one here. Factor that difference of squares, 16 minus a squared. Just work on that one right now, and when you have an answer, go ahead and type it in. You have an answer. Okay, good. A lot of you have come up with 4 minus a times 4 plus a. Okay, what you recognized was that 16 was my first square. So because 16 was my first square, I needed to put that into the first position, and then my a squared came next. Now, I have had students rewrite this as negative a squared plus 16. Then they'd factor the negative 1 out of this thing and call it a squared minus 16. Now they have a difference of squares that they rewrite as a plus 4, a minus 4. So there's lots of ways to visualize this one. One is to look at it like this, with the 4 minus a, 4 plus a, and another is to look at it like this, where I just kind of want to rewrite it in a way that I'm familiar, where these variables come first. But if you do that, we often have to look at factoring out a negative 1. Now this second one, is it a difference of squares? Is j squared minus k to the 4th, is that a difference of squares? What do you think? Yes or no? Is that a difference of squares? Why don't you pull in, is j squared minus k to the 4th, is it a difference of squares? Okay, well, we have some indecision here. Some say yes, some say no, and some aren't sure. And then I've had a couple people type in. This is a difference of squares. The idea here is that j squared we recognize as a square. But k to the fourth is also a square. And Ramel, you put in j minus kj plus k, which is really close, but the idea is k to the fourth. As a perfect square, k to the fourth is k squared times k squared. So what happens then, as Jane pointed out, then we're going to take j squared would be j, and we would have k squared, and a j, and a k squared. And we have to look at this again as sum and difference. So whether you write plus and minus or minus and plus, it doesn't matter. Because the idea is that we're looking at this, and we can see then that we would have, as a middle term that would drop out, negative jk squared and positive jk squared. Okay, good. So we can actually factor that. Excellent. That's a little about difference of squares. I want to finish off then with some different trinomials. Two different looks at some trinomials here. And this first one here adds in kind of an interesting component because we have another variable, t squared, in there. And we have this middle term of st. So I'm going to look at this and I'm maybe going to think of using grouping to solve this to try to figure it out. I want to figure out what multiplies. Okay, again, I'm going to figure out what multiplies to a 24, but what adds to a negative 10. So go ahead and just give me the numbers of what multiplies to a negative 24 and adds to a negative 10, or sorry, positive 24, and adds to a negative 10. Okay, good. I see negative 4, negative 6. Okay, and then I see negative 12 and 2. So negative 4 times a negative 6. Okay, changing our mind now. Negative 4 times negative 6 is that positive 24 and does add to a negative 10, or negative 10. Negative 12 and 2 is often kind of the common misconception one. That multiplies to a negative 24. Okay, so we're not going to use that one. So let's use negative 4 and negative 6. I'm going to rewrite this as s squared minus 4st minus 6st plus 24t squared. And again, all I'm saying is, well, I know those middle terms, that we have to do something with this negative 4 and negative 6. So I'm going to rewrite that middle term like I've done before, so I can create a factor by grouping situation. So I'm going to group those first two terms. I left myself a little bit more room this time, so I could group my second two terms. Again, notice how I put a plus sign in between there because I have that third term that's negative. I don't want to change my problem up here. Grouping now, I'm going to take an s out of the first term, getting s minus 4t. And out of my second term, well, I have a negative 6 and a t that are in common. And what's going to be left is s minus 4t. So factor by grouping then shows us that x minus 6t times s minus 4t is my answer. Okay. Some people also look at this and say, well, I know that I have a t squared at the end of this thing. So because I have a t squared at the end, I know that I need to find some variables like t times t to give me a t squared. I just need it in my last position, right? In FOIL, I need it in my last position. But that's one way we can look at factoring this. What about this second example, our last example for today? H to the fourth plus 3h squared minus 18. How are we going to factor this thing? We have an h to the 4th. Okay. First we can ask, is this a difference of squares? Well, not quite. It is a trinomial. Okay. How are we going to factor? And I want you to kind of think about it, maybe put some ideas out there. You have to think, what's going to multiply to h to the 4th? What's going to multiply to h to the 4th? Also, what's going to give us a negative 18 and a positive 3? Any ideas as you're working on these? Okay, good. Well, Wendy has told me that h squared is going to multiply to h to the 4th. We're going to be looking at a negative 3 times a positive 6. Okay, good. I saw a lot of other people. Good. French is kind of on the same idea here. So if I set up my binomial, then I can think, well, h to the 4th, then I know that h squared times h squared is one possibility. Good, and Ronmel and Jane have said, yeah, I think it's going to be h squared. I'm going to use those terms, minus 3 and positive 6. Leaving me, if I want to, as I always do, check my answer through distribution. I have h to the 4th plus 6 h squared minus 3 h squared and minus 18. So I can see that those h squares as leading terms does give me to h to the 4th. 6h squared and a negative 3h squared leaves me with a plus 3h squared. And my constant of a negative 18 still remains. Very nice, very nice. Good. Well, thank you all for your participation today. I've been really happy to be working on these live lectures and that so many of you continue to come. I hope that you find them helpful through your journeys in the Math MOOC. And we have one more live lecture, which will be next Monday. So I look forward to seeing you then. Thank you so much for coming, and I will stick around if you have any questions on this or any other content. Yes, thank you.